mentioned, my name is Jillian Augustine, and I'm a data scientist at Mondi. And today I'll be telling you about data-driven process optimization that we do at Mondi. So first, today I will talk to you about a range of topics. First, industrial IoT, so industrial Internet of Things at Mondi. Then I will talk to you about what soft sensors are and how we develop them. And then finally, I will briefly talk about model management as well. So I'm pretty sure there are some of you in the audience who have heard of Mondi before, at the front, my colleagues. But for those of you who don't know, Mondi is a global packaging and paper company. There are around 26,000 employees at the company, and we have around 100 production sites all across the world, with main focuses in Europe, North America, and in Africa as well. We also have a premium listing on the London Stock Exchange, and just to throw a number out there, our revenue last year was almost 7.5 billion euros. So we're quite a big company. And even if you might not have heard of Mondi before, you have definitely been in touch with our products. And this is because Mondi serves a huge range of industries. So from the agricultural industry, also the medical and pharmaceutical industry, and then there are the maybe more obvious choices, so office and professional printing industries, so office paper. And then personally, my favorite industry, which is e-commerce, and that's because I hate shopping. So I buy everything online. So when I buy things, it often comes in a cardboard box, which has been made by Mondi. So as was mentioned, I'm a data scientist. I'm not actually located at our production sites. But when I go into the production sites, one thing I notice is what's going on. There's so much going on in the factories. There is a lot of noise, there are a lot of machines going really fast, a lot of levers, a lot of gears. There are also a lot of machine operators who are looking very intensely at displays, displaying numbers and charts, telling them information such as which product is currently being created or how fast the machine is running. So this, for me, is really interesting because when I see all this happening, I see potential for data, and I see potential for data collection. So on the topic of data collection, in our factories, we have tens of thousands of sensors monitoring the current state of the factory in real time. So we are talking about approximately 40,000 sensors. In addition to this real-time data, we also have non-continuous data, often in the form of quality control laboratory testing. And altogether, this brings together petabytes of data, so you can really say that we are talking about big data in this case. And whenever there is big data, it follows with big data challenges. So I'd like to list a few of the challenges we have here with manufacturing data. So often, manufacturing processes can take months at a time. So for example, you harvest trees maybe in autumn time. You could store the wood over the winter, and then only in spring do you use this wood to produce paper. And so this means that you have different data points which are very relevant to each other, which are spread over a huge period of time. And combining these different data points can be a challenge in itself. We also have the typical ETL troubles or ETL challenges, such as our machines are constantly running, they're highly secure, the data is highly secure. So it's a question of how do we extract the data from these machines, bearing in mind we have to be extremely, extremely careful to make sure that nothing on the operational side is affected by how we extract the data. Also, data can be collected up to a scale of on a microsecond scale. We need to decide in the transformation case, how much of this data do we take? Do we take averages of the data? Do we take snapshots of the data? This is also something that we consider. And finally, the load part of data is a question of how do we store this data? Do we store it, what kind of systems do we store it in? Do we store it centrally? Do we store it locally? And also, how do we get this data out of these storage systems so that our digital team can work with them to drive data-driven insights? Now, Mondi is a company which has acquired many companies over the years. And in the different companies and different production sites, they work very differently. So they might have different machines in practice. They might store their data in different ways. And if you're a data scientist or a data engineer, you know that this is a big pain point for you. So standardization of the data across production sites is one of our key first challenges. And then finally, whenever there is data, there is always missing data. I don't have much to say about this point, but it's a point that everybody can relate to, and I think it's definitely worth mentioning. Now, at Mondi, I work as part of the group digital transformation team. This transformation team is based in Vienna, and we work in a local and central approach when we work on a daily basis. So on a daily basis, what we do is to create digital products for the different businesses. These are often in the form, for example, of machine learning models, forecasting, or advanced statistical analysis. And in the digital transformation team on our side, there are data scientists and engineers who are the main technical skills in the team, and we work on a variety of topics. So we have focus areas on soft sensors, which I will talk about today, machine performance, and also predictive maintenance, which is actually the topic that I work on. And then on a local level, we work in close collaboration with different people in the plants and mills. So for example, the factory managers, technical experts, and machine operators. This exchange with them is essential so that we understand the data and that we can get the most insights from it. In my case, I work very closely with maintenance managers. They can provide me with data regarding what parts of the machine were breaking and when, what parts were repaired, why the machine was stopped. This data is essential for the topic of predictive maintenance. And finally, we work with continuous improvement specialists whose goal is to optimize processes across Mondi. So now I will move on to one of our focus areas and talk to you a bit about that, and that is the area of soft sensor development. So this raises the question, what is a soft sensor? So as the name might indicate, there are soft sensors, so there are also hard sensors. And hard sensors are something that you might be a bit more familiar with. So hard sensors are the things that you tend to think about when you think of what a sensor is. These are devices which can continuously measure certain aspects, such as speed of machines, torque, so rotational force, or also temperature of machines. And these are things which are measured on a continuous basis. But it's also, hard sensors are also used for non-continuous measurements, for example, for measuring quality. In the case of quality measurements, these measurements tend to be taken towards the end of the process because they are non-continuous. Often, also, the laboratory testing takes a lot of time. It can take up to an hour or 90 minutes in some cases. And this time delay causes less control of the process, of the quality process. So, for example, in some of our factories, we are making kilometers of paper every hour. And say you are a quality control expert, you get a sample of product, you test the quality on it, and then an hour later you get a result which says, this product is of insufficient quality and cannot be used. It's not suitable for sale. So in this past hour, you've been producing kilometers and kilometers of paper which you cannot use, you cannot sell, which is a huge waste of money. And this is where the real advantage of soft sensors comes in. So soft sensors are also known as virtual sensors. They often take the form of machine learning models, for example, of product quality. And the benefit of soft sensors is that predictions can continuously be made. So the many sensors that I mentioned that are present in the factory can be used to develop machine learning models to predict quality. And this can really cause a reduction in the delay to action of the process experts. So as soon as they see that the quality of the product is going down, then they can make changes to the machinery so that the product quality increases. So how do we go along building a soft sensor? So the first point I would like to highlight here is communication. Communication between the data team and between the technical experts in the factories is essential. And this is something which happens throughout the model creation and model management process. So if you know a bit about Kaggle competitions, you might know that one key feature of Kaggle competitions, or what often distinguishes good models from the best models, is feature engineering. Feature engineering often requires deep technical knowledge to understand which insights are the most useful, or which features are the most useful. So our data team sat down with the technical people in our team and discussed which types of variables among these thousands of variables should be combined in which ways, and also which extrapolations can be made from these, which aggregations of these. So, for example, rolling averages, is the standard deviation more useful than the actual absolute value itself? And this collaboration with process experts led to an expansion of the data set to over 80,000 variables. Now, I don't know about you, but when I, as a data scientist, see a data set of 80,000 variables, my first thought is, I do not want to build a model with 80,000 variables. So the next step we go on to is feature selection. So in this case, our soft sensor team used recursive feature elimination, both linear and nonlinear, to get an idea what was the optimum number of variables to use when creating these models. They also then use various different algorithms, so in a data mining context, to rank the different variables from most to least important. These different algorithms have various different advantages and disadvantages. So, for example, some allow you to see the importance, see linear correlations between variables, nonlinear correlations, interactions between different variables. And they took the information of this ranking and they combined it together to create a final list of approximately 100 variables. So the next step was to go on to model selection. So in the team, with this reduced data set of approximately 100 variables, they compared various different machine learning algorithms. So they went from the classic and most simple algorithms, such as linear regression, to some slightly more complex algorithms, such as boosted decision trees. And during this process, they constantly applied what is known as cross-validation. For some of you in the audience will know what this is, but for those of you who don't, I thought I would give you a brief overview of this. So when we create a machine learning model, we have a whole set of data. The first step we do in this case is to split the data into a training set and a test set, normally in an 80-20 split. And then we take the training data and we split this further into folds. So in this case, as you can see on the right, there is a representation of 5-fold cross-validation. And from these 5 folds, we can split, we can create different subsets of data, and we perform and we apply these algorithms to the different subsets of data. So for example, in the first subset, split 1, we use folds 2 to 5 for training, and we test on fold 1. Whereas for split 5, we use folds 1 to 4 for training, and we test on split 5. And in this case, this then allows us to have 5 different sets of predictions from which we can calculate 5 different accuracies. And then these accuracies are combined together to find the mean accuracy, and this can be an indication of model performance. But this is not the main benefit of cross-validation. What I consider one of the main benefits of cross-validation is that it allows you to see the variance of your model. It gives you an indication of how your model would perform on data that is not seen before. Normally we use this process in the case of hyperparameter tuning. So for example, in cases of models which have hyperparameters such as random forest or decision trees, we can use this to decide which hyperparameters allow for the best model. And also we used cross-validation to compare the different models. So say, for example, you have model A and model B. And model A has a higher mean accuracy or whatever performance metric that you are measuring. And model B has a slightly lower mean accuracy after cross-validation. But what you might see is that for model A, the variation or the standard deviation of these accuracies could be huge, which means that sometimes it performs really, really well, and then other times it doesn't perform well at all. Whereas if you compare this to model B, you might find overall the average accuracy is lower, but sometimes it's a little bit higher, a little bit lower, but it's pretty robust in how it predicts accuracy. It's not high sometimes and low sometimes. And in cases like this, it can actually be beneficial to go for the model with slightly less accuracy, but it's reliable, and you can really trust this information more. And then finally, once a final model is chosen, the test set, which was extracted at the beginning, as I mentioned, this extra 20% is used to generate a set of predictions and therefore an estimated accuracy, which can be used as an estimate of performance of the overall model. So these were the steps that were taken in model selection. So here is a little example of how the model actually performs. And I'd like to draw your attention to 2 points here. So on the green line, so that's the one, the bottom right for the target. You can see the target variable, and the blue line is for what the model predictions were made. And as you can see on the box on the left, sometimes, so many of the times, the model is able to accurately reflect the highs and lows of the quality of the product. So for example, you can see that it's been able to identify this peak which goes up and then goes down again. Whereas on the other hand, in the right-hand box, you can see that the model's not being able to capture this dip which happens and then when it goes up again. And in these cases, we need to look a little bit closer at the data and how the model is performing. So the team identified areas of low performance of the model. They took these subsets of data and created data mining models on these to identify which were the important variables affecting the performance of the product in this subset of data. And then they look at these variables and see if they were included in the initial model, and if they were not included, then they ask why. And sometimes the initial feature selection list was increased, so it's very much an iterative process to fine-tune and work out these small tweaks in the data. So now we have a model. It predicts well. We want to actually use it now. So now we move on to model deployment. So here I've drawn a schematic of how we deploy models in production, often is the case in the manufacturing industry. So on the top left, you see a barrel and a cog. This represents the paper-making process and the machinery. So on a per second basis, data is sent from the machinery, from the sensors, to the distributed control system. This, also known as the DCS. This can be seen in a way as the brain of the factory. And then also on a 1 second basis, the DCS sends this information to an SQL database. Now, the SQL database collects this information over a period of 5 minutes, and once every 5 minutes, it sends this new data to the machine learning server where the model has been deployed. And then the model makes predictions on the new set of data, and then also on a 5-minute interval, it sends these predictions back to the DCS. And these predictions is actually what the soft sensor is. It is a model. It's predictions of quality based on parameters coming from the machinery process. And if you compare this soft sensor to, for example, the hard sensor, you can really see the advantage of knowing the quality on a faster basis. So then these soft sensor predictions, as well as hard sensor predictions when necessary, can be relayed to the screens in the factories so that the machine operators can see it directly, and so they can make adjustments if necessary on a very short scale. And additionally, the soft sensor measurements can be used in the process of advanced process control to actually automatically adjust how the machines are running, how the machines are managed, to automatically reduce, for example, increase the quality of paper if there is indication that the quality of the paper is decreasing. So this is what we have done, and this could be defined as a successful pilot project. So now, briefly, I would like to talk to you about model management. So we've seen one successful pilot project. The data team has done their job. They're very happy. They move on to another project. What happens to the model that they deployed at the first place? So there is a concept called concept drift, which happens with data because data is continuously changing. And in concept drift, some of the assumptions that you might have built your model on no longer hold, and this results in model degradation. And in this case, what we do, we have set a quality threshold, and if the model degrades to this quality threshold, there is a trigger, and then there is automated retraining of the model using data which has been accumulated during the time that the previous model was running. And then, as you see, once the model is retrained, the model accuracy increases again. But what I want to point out here, that as soon as it increases, it naturally starts to decrease again. So this is a constant process which is happening. So what happens when this goes on and on a few times? So here I show a very similar diagram to the one before. So at point 1, you have a successful model training using data after the model has degraded to a point that it has triggered the alarm of the quality threshold. Then at point 2, sometimes there is some sort of major change in the model's assumptions. For example, the distribution of one of the variables changes. This can happen for a variety of reasons, such as machine repair or machine cleaning, or even in some cases, the sensor is now measuring something which you did not anticipate that it would measure. And then in this case, when the model degrades to the point that it reaches the threshold, the retraining is triggered, but it's inefficient. So you don't get the standard increase in model accuracy you would expect. And this is when our data team gets notified. And we get straight back in there to have a look and see what's going on and find out what is the problem. And often, as a result of this, the process that we take is to do remodeling based on the performance of the model. And this is what you see. Sorry. So in step 4, we go back in, and then step 5, you have redeployment of a new model which has been developed by the team, and then the model accuracy then goes up again. So this is what what allows us, this monitoring of model performance, retraining and remodeling is what allows us to keep an overview of the models we have. And I'd just like to finally mention that, for example, we might have a model in one plant in a pilot phase. We would then have a proof of pilot phase in a second plant. And then our aim in the digital transformation team is to roll this model out to all the other sites in that business area. And I want to emphasize that this is a key point in which we consider digital transformation. So at this point, this is when the use of the soft sensor has become the standard practice of how that factory functions. And this is when we've reached successful digital transformation. And with that, I would like to say thank you, and I'm happy to take questions.
Thank you. Thank you, Jillian.
Thank you.
OK, we do have some time for questions, so let's get going. The first one right here. As the core of your business is not data science, are you working with external partners or doing it internally?
So we are doing a bit of both. So we are hiring. So we have had a digital transformation team since just for under a year now, and we are developing digital team of data scientists and data experts. But we are also working with external partners as well for some projects. Yeah.
OK, thank you. And what kind of technology do you use to gather machine-level data, and where do you store it?
So there are many. So there are a few typical sources of machine-level data. They are very technical. They're very much standards in the industry. One example is vibration sensors. And vibration sensors actually take small measurements of a probe, and then from this they can work out how much a piece of machinery is vibrating. And we store it. The storage case depends on the IT maturity of the site, you could say. Sometimes it's stored centrally in secure SQL databases. In other times, it's stored locally if they have good infrastructure there.
OK, thank you. How do you identify potential use cases for machine learning in business-related processes?
So there are many different use cases. And as it mentions there, the challenge can be trying to work out which are the use cases that you can make the most out of. And for us, we are a very data-driven business. So it really comes down to how can we optimize the process and what can we save from doing this? So down to the number crunching and how much money can we save from this?
Makes sense.
Yeah. Mm-hmm.
Time for one more, I think. OK, let's do this one. How much is AI used at Mondi in real life? So is it all the machines around the world or just a few experiments?
So as I mentioned on my last slide, AI is developed in an experimental way, in a developmental way, but the key focus of every developmental project is to end in a digital product, which means that all the development that we do in the DX team finally goes into rollout. So so for this, I would say all the machines around the world.
Very nice. Cool.
Okay.
OK, thank you very much.
Thank
Another
you.
round of applause for Jillian, please.
Okay.